Hi, the section 11.2, the model specification and output. So now that we study the multiple linear regression model. So it's similar to chapter 6, but we have more than one predictors. So consider multiple predictors, x1 to xp, to predict a continuous response y. And the multiple linear regression model assumes y is equal to a linear combination of x1 to xp. So we have any linear combination. And you can see that this is linear in terms of x1 to xp, but actually the more important part is that it's linear in terms of beta naught to beta p. For example, if you want to include square of x1, then it's possible to put that term by using, I don't know, maybe gamma 1 or something. And it's still it's linear with respect to beta. And we are doing statistics and we are estimating these parameters. So it's totally fine to have this quadratic term also. But it's linear combination of our predictors. The predictors can be something square or something cube or something more complicated. And here again, the epsilon is IID random variable with expectation 0. Yeah. In some more advanced settings that we consider non-IID case, but in this course, basically we assume epsilon is IID. Yeah, and suppose that we have n observations, and then we can write the equation in number 2. So this is the same as number 1, but we just specifically mentioned that this y is the jth observation of y, and this is the jth observation x1 value to xp value. And this is the jth error. If we have n observations, then we have j is equal to 1 to n. So example. So we want to predict the house price by the square footage and the year built and the number of bedrooms and the number of bathrooms. Then we have y, the price as y, and the square footage and the year and the bedroom and bathroom are x1 to x4. And x3 and x4 are discrete variables. So that you cannot have the 2.3 bedrooms. That's just an integer, probably from maybe 1 to 5. So we can regard this variable as factor variable. In such a case, we don't have to assume the linear relationship between house price and the number of bedrooms. So factor, so that means okay, so if suppose we only have x3, then y is equal to beta naught plus beta 3 x3. So this is the usual linear model, but if it becomes factor, x3 becomes factor, we can say that the beta 3(1) times indicator variable of the bedroom houses, indicator variable for 2-bedroom house, 2-bed, and the beta 3 times indicator variable of the 3 beds, and so on. So suppose we only have up to 3 bedrooms, then we can do this. Then we can see that this relationship between the number of bedrooms and the parameter doesn't have to be linear. So beta 3(2) is not necessarily twice as large as the beta 3(1). So in linear model, always the additional bedroom, the 3 larger. So y value gets beta 3 larger. But here we can set, for example, that this is, for example, $10,000 higher, but the second bedroom only the value of 5,000, and the third bedroom, maybe I should say the 10 plus 5, so maybe 15, and we have 19 or something. So we don't really have to make this the proportional to the number of bedrooms. Then the model becomes more flexible, but we have more terms, so more complicated models. Yeah, and this is the matrix representation. So remember that this is basically the same as the simple linear regression case. So y is the vector of y values, and x is the vector of x values. So for simple linear regression, we only have 2 columns. But here, we have the p+1 columns if we have p variables. Then beta becomes larger. Originally, in the simple linear regression, only have the beta naught and beta 1. But now that we have up to beta p. And still, we can write y is equal to x beta plus epsilon. And everything is the same to prove, for example, the estimate of beta hat or the estimated the variance of epsilon and so on. So you can, deal with it exactly in the same way. So epsilon is y is equal to x beta and so on. So, and the least square estimator. So now that we would like to discuss how to estimate beta, and the least square estimate beta hat is the minimizer of epsilon j square, sum of epsilon j square. So that is this term. And this is actually written as, including this square term and the summation. So it can be written as the y minus x beta, the transposed minus times y minus x beta. So so this is n by 1. So y is the n-dimensional vector, and x is n by p+1, and beta is p+1 by 1. So in total, n by 1. So actually, we transposed it. So 1 by n and n by 1. So this is scalar. And this expression is exactly the same as simple linear regression. So that's why we can derive exactly the same formula. Beta hat is equal to x transpose x inverse times x transpose y. So for simple linear regression, it's possible to prove the all theorem from scratch, just using the all elements. So we can name the all elements, x1 to xn and y1 to yn, and using the summation symbol and some product of some vectors, we can product of some numbers, we can derive this. But the more than one predictor, it's almost impossible to derive everything without matrix. So just remember this formula. Yeah, so even in our PhD qualifier in statistics, sometimes students try to solve without matrix form, so that makes more complicated. So linear model is always easier to deal with when we use matrix representation. And we can define y hat fitted value or epsilon hat residual in the same way as simple linear regression. And also the formula for variance of beta hat and adjusted R square and predicted interval, confidence interval, those are obtained almost exactly the same way as simple linear regression.